All right, class, so today I'm going to go over some examples from Chapter 7 about estimating population means. The first thing I want us to recognize is that there's a couple of symbols we need to be familiar with. So I'm going to have z sub alpha 2. That's the z-score separating an area of alpha 2 in the right tail of a normal distribution. What does that mean? Here's our normal distribution. Here's z sub alpha 2. And then the area in this right here, this area is going to be alpha over 2. Mu is our population mean. Sigma is our population standard deviation. X bar is our sample mean. S is our sample standard deviation. I forgot that one. And we're going to be working to estimate these population means. So we're going to be calculating confidence intervals, okay, which require a margin of error. So E is our desired margin of error, and N is our sample size. It's also just our margin of error. Sometimes we set it and sometimes we don't. So remember that the confidence level plus alpha equals 1. So if I want to construct a 99% confidence interval, alpha is going to be 0.01. So this is for a 99% confidence interval. If I want to construct a 95% confidence interval, alpha is going to be 0.05. And if I want to construct a 99% confidence interval, alpha is going to be 0.10. These are the critical z-table values associated with alpha divided by 2. So remember to keep this table readily available when you're looking for a confidence interval. I don't know why I wrote that as CL. It should be CI. When we're looking for a confidence interval, okay? So here are two equations that you will be given on exams. This one is calculating the margin of error for sample means, and this one is calculating your sample size. So if I wanted to have a specific error, I would calculate my sample size. Remember that a confidence interval is a range of values likely contain the true value of a population mean. So when I'm using this to calculate my margin of error, it relates to my confidence interval, okay? And I have to choose the z level, the z value that relates most closely to my confidence level. So if I'm constructing a 95% confidence interval, that means that 95% of the sample means lie within 1.96 standard deviations of the population mean if the distribution of a sample means is normal. For a 99% confidence interval, all sample means lie within 2.575 standard deviations of the population mean. And for a 90% confidence interval, it would be the same thing, except now I have a z value of 1.645. So that's the number of standard deviations within the population mean. So here we have our 95% confidence interval, right? Just about 2, 99, and 90 would be right about here. So let's work through a couple of examples of constructing our confidence interval, which is found by taking our sample mean minus our error and our sample mean plus our error. Okay, this means my true population mean is going to be in between these two values. So let's consider the daily protein intake for a sample of 267 men with a sample mean of X equals 77.0 grams and a sample standard deviation of 58.6 grams. Okay? I'm going to find the margin of error for a 95% confidence level or interval and construct the 95% confidence interval. Okay? And then we're going to compare that to our recommended dose for men, which is 55 to 60 grams. So I have that error equals Z sub alpha 2 over my standard deviation over the square root of n. So I have my error to be 1.96. I got this value from our table because it's the z-value associated with a 95% confidence interval. In this case, alpha is 0.05. So I have 58.6 over the square root of 267, and I get 7.03. So I'm going to go ahead and round that to 7. So I'm going to construct my confidence interval. So I take my sample mean minus my error is less than our true population mean, which is less than our sample mean plus our error. That gives me 77 minus 7 is less than true population mean. And, oh, I messed up my notation over here now, didn't I? And 77 plus 7. So I have a confidence interval of 70 to 84. Now, how does this compare to the recommended intake for protein for men? It's a lot higher, right? So that's something to keep in mind, that our sample is way above the recommended intake. So this is a way we can compare intervals. Next, let's look at some women. So the figure below shows the daily protein intake of a random sample of 264 women. The mean of this data is 59.6 grams, and the standard deviation is 30.5 grams. So we're going to estimate the population mean and give a confidence interval. So we use this value to estimate our population mean. And then we'll give this 95% confidence interval, which I find by taking our error times z sub alpha 2 times our standard deviation, which in this case is s, over the square root of n. So I have 1.96 times 30.5, which is my standard deviation, over the square root of n, which is 264. I plug this into my calculator, and I get 3.68. Okay? So I'm going to go ahead and round that to, I'm just going to leave it as 3.68. So I'm going to take my sample mean minus my error to my sample mean plus my error. That's going to give me 59.6, our sample mean, minus 3.68 is less than our true population mean, which is less than 63.28. Sorry, I skipped a step, which is less than 59.6 plus 3.68. So that's going to give me from 55.92 to 63.28. All right, class, so now we're going to look at how to determine what type of sample size we need. So let's say you want to study housing costs in a rural county by sampling recent house sales. Your goal is to provide a 95% confidence interval estimate of the housing costs. Previous studies suggest that the population standard deviation is about 7,200. So what sample size at a minimum should be used to ensure the sample mean is within $500 of the true population mean, and then we'll check $100 of the true population mean. Now we're using a 95% confidence interval. So I know my my sample size, n, equals z sub alpha squared times my standard deviation over our desired error squared. So I'm going to take 1.96 times 7,200 divided by my error and square it. That gives me 796.59. Now, we're sampling houses, right? You can't have 0.59 of a house, so we need to round this up. You're always going to want to round it up. So you've got 797 homes, okay, that we would need to survey. Now, let's say I wanted to have an even smaller error. I wanted an error of 100. So I would calculate this again, but now instead of my error being 500, my error is 100. Now, because I'm dividing this big number by something smaller, my sample size is going to increase. I actually get 19,914.85. So we're going to have to round up. So in order to get a error that's within 100 of the true population mean, we would need to survey 19,915 homes. That's a lot of homes.